That tracks.
I watched part of it.
All right.
Didn't have time.
It's 6 o'clock, so I just wanted to start. And we can go ahead and get going. Do I need to mute this?
It's pretty cool how
I'll mute
you
it.
got this set up.
Thank you. I just want to make sure you don't see this too much. Give me 1 second.
Oh yes.
You already know I'm a streamer, dog.
Dude, nice.
Can we move this? Maybe. There it is.
Mission a little bit.
You used OBS on your mission?
Yeah.
That's wild. For what? Just like the screen recording?
Yeah,
Yeah.
like a music video.
Nice. Welcome to Midterm Review number 1, ECON 378, Summer 2022. This one's going to be a little bit different because as opposed to covering like an actual review for the test like I did in the last term, spring of 2022, this term the mini lectures exist, and so there's not really any point in me just reiterating that again. So here in the class we have both Spencers, and that's it. And we've asked people to bring questions. Hopefully, if you're here watching, which it doesn't look like anybody is yet, but if people jump in, they'll be able to ask questions in the chat. And the tricky thing that I did is I made it so you have to be a subscriber to chat. So.
Okay.
But you can subscribe right then, you know?
Like a YouTube subscriber or what?
Yeah, subscribe to the channel, right? But anybody with a Google account can subscribe, you know?
Okay.
So as soon as you're subscribed, you can chat just instantly, right? Looks like we got 1 viewer, so that's good. So let's just start taking questions, right? Who's got the first one?
I do.
Hit me.
Okay, sometimes the like probability or combinatorics questions get me.
Okay.
So there's an example on page, oh well, I guess, this was an example in class.
Okay.
But it's the number of ways to place 10 students into groups of 3, 5, and 2. Into groups of 3, 5, and 2.
Yeah, okay.
That makes sense.
The number of different ways, so we're just going to review really quick a little bit of combinatorics then. So just really quick, if I have n factorial, that's going to be the number of ways you can order n things, right?
Mm-hmm.
And that's a permutation, just factorial by itself, right? If I have 3 books, right, and I want to order them, I could go ABC, I could go BAC, I could go, let's think. I could go ACB, I could go BCA, I could go CAB, CBA, right? And that's 6 different ways you can order 3 things, which just so happens to be 3 times 2 times 1, which is 3 factorial, right? Easy peasy, nothing too crazy there, right? But then it's like, well, how many different groups of X number amount can I pick from this set of, you give the example of 10, right?
Uh-huh.
So the way that we denote this is either like this, we'd do like 10 pick, I don't know, 3 just to start, or, 10 choose 3. These notations are basically equivalent. But the way that they work looks like this. I want to take 10 things and give them, how many different ways can I assign 10 things to 3 spots if I don't care which spot each person ends up in, right? So like the order, once we get into combinatorics, order doesn't matter, right? A group of Spencer, Spencer, Tommy is the same as the group of Spencer, Tommy, Spencer, right? Same group. And the way that this works, this is just a mathematical thing, right? This is the number of unique combinations. So let's say, for example, well, the number of way, I'm going to be honest, I don't understand exactly why this math works the way that it does,
Okay.
exactly like this. But the way that you do it is you do the top number factorial, and then you divide it by the bottom number factorial times the top number minus the bottom number factorial. That's just how it goes. And then the thing that you notice, right, and let's just write this out, 3 factorial, 7 factorial. If I were to just write all of this out, that's 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8 times 9 times 10 over 1 times 2 times 3 times 1 times 2 times 3 times 4, hello and welcome, times 5 times 6 times 7, right? And so the thing that you'll notice is that whatever number is bigger on the bottom, you're going to want to cancel out, right? So you can go 1, 2, 3, 4, 5, 6, 7. And that leaves us with just 8 times 9 times 10 over 1 times 2 times 3, which is equal to, 8 times 9 times 10. And we could simplify that and make it easier, right? But I have this calculator here. It's 120. Welcome, welcome, everybody. We got Alec and we got Jayla? No. Rachel, sorry. All right. So there's 120 different groups of 3 you can make from a set of 10 things, right? And then the question is like, okay, knowing that, is there any way that we can use this to do something cool, right? Let's say, for example, in fact, let me not erase all of that. Let's just move on to another page. We're talking about combinatorics, if that wasn't too clear, So let's go ahead and take the same thing. Let's say that we have 10 students who applied for like 3 positions, right? Maybe like, I don't know, at some job. Maybe the Chick-fil-A. Everybody wants to work at the Chick-fil-A, right? And let's say, for example, that we have 5 guys and we have 5 ladies, right? And what ends up happening is that, the only people who get hired are guys. So we end up with 3 guys and none of the ladies filling these positions. And we want to know, right, like Chick-fil-A, they're saying they're some kind of like equal opportunity employer, say, one might suppose, although maybe not necessarily with Chick-fil-A. But maybe we want to know if it's truly random and if all these students are equally qualified for this job because it's a Chick-fil-A job and they're all at BYU, right? If they're all equally qualified, what's the chance that this outcome happened at random? Maybe, right? Maybe we want to see, did they actually randomly assign this? Or was it like they specifically were biased towards picking the guys? And so one thing that we could potentially do is we could figure out the number of different ways in which this actually happens and divide it by the number of different ways that we could assign 10 students to 3 positions, right? So over here we know that there's 120 different like groupings of students that could get hired now, right? But let's narrow it down and see what fraction of those 120 things gives us this specific outcome, right? So what we want to know, hypothetically, is what's the number of ways that you can pick 3 guys from a set of 5 of them. Take that and multiply it by the number of ways that you can pick 0 girls from a group of 5. By the way, that number's 1. There's only one way to pick 0, right? And then let's just divide that over the ways that you can pick 3 students from 10, right? These are the questions that I'm assuming you were having the most trouble with when you were asking the question, right? Mm-hmm. Is this question of like, how do I set up the ones that actually give me probabilities? Yes, no, maybe so?
There's a slightly different situation, but...
Okay. Well, let's just finish this one really quick and then we'll see if we can't cover really quickly the slightly different situation that you've got, okay? Just really quick, this is 5 guys, this is 5 ladies, 5, and then we got 3 hired and 0 hired, 10 students, 3 hired, right? And not to put too fine a point on this, but notice that these top numbers add up to this 10, these bottom numbers add up to this 3, and that the smaller numbers have to be on the bottom. It doesn't make a lot of sense to have the bigger numbers on the top. just by virtue of like this thing right here, you'd get a fraction, which doesn't make any sense, knowing like what these are actually supposed to be. This turns into over 120. 5 factorial over 3 factorial is, it's actually just 10. Because it's 4 times 5 over 1 times 2, because it's 5 factorial over 3 factorial, 2 factorial, right? So this is 10 over 120, or 1/12. So, like, in 1 out of every 12 possible groupings of 3 students that you can hire from this group of 10, in 1 out of every 12 of those, you get this outcome up here at the top, which is pretty cool. And then whenever the question asks you, like, are they discriminating, or like, is this a thing that makes sense, you can go from there, right? So then what's the specific angle that you were thinking of?
So there was an example in class that was like assign 10 students
Mm-hmm.
into 3 groups, a
Yeah.
group of 3, a group of 5, and a group of 2.
Oh. Group of 3, a group of 5, and a group of 2. Well, I have no idea how we'd do that. That was in class?
Yeah, I mean, I usually just
Oh,
copy it all
okay,
down,
okay.
but I didn't understand it, so I was like,
Okay, that makes a lot of sense. So, intuitively, if I'm trying to assign 10 things to 3 spots, I'm actually assigning 10 things to one of 2 different groups. Either the spots 3 or the not spots 7, right? So if I wanted to break it down even further, I could assign maybe I have 10 students and I actually want to assign, 5 to the Chick-fil-A and 2 to Choices and 3 to the Taco Bell, right? Well, now I have all of the groups, and because the groups are exhaustive, I can turn that into something like a 10 factorial over 5 factorial, 2 factorial, 3 factorial. That's just how these pick and assign things work. You're not going to see that again. I've never seen it before, which 1 shows you how much I'm paying attention in class while she's giving the lecture, and 2, and 2 hopefully explains to you something about the relevance of this. Everything that we're doing right here before the lecture, other than like expected value variance, covariance correlation, and like the basics of regression, everything else you're really not going to see much of later, because we're just building the foundations of like probability theory, so that hopefully the things that we're about to introduce, like continuous density functions, make more sense, right? So don't worry about this, but that is cool. That makes sense. I learned something now too. Cool. Let's
Can I ask one question about
yeah.
that real quick? Sorry.
This one on the left?
Yeah.
Yeah.
So the one she did in class today with the bachelorette, I didn't understand like why that fit into the way she did that.
Okay, what did she do in class with the
So she said
bachelorette?
that there were 6 made it to the finals, and then 2 had Beards, 4 she put in hometowns, and then why is the final 4 with Beards? So then the question was, well, I don't know, the answer was like E of y is equal to, and then she set it all up, but I was confused how she set it up.
So
Okay.
the way that she did it was,
Yeah.
she set y equal to the Beards.
So
And she
so
wanted-
what so hold on, what's the question again?
The question is, I guess in a group of 6,
Mhm.
4 are chosen,
Yeah.
and 2 of the 6 have Beards.
Okay.
So it's like, what are the odds? Well, the second one is, what are the odds that at least one has a beard? But the first one was, what's the expected value of Beards and the variance of Beards?
Yeah, that was kind of a trick, because I don't remember us ever doing expected value with.
Yeah, we've never
Yes.
done it from the
We're gonna
very
go
beginning.
ahead and skip that one. That's
Okay.
you don't need it.
Okay.
As long as we know.
Yeah. A question that looks like that is not going to show up, and with these combinatorics and stuff, you're really not going to see that.
Yeah, 'cause
So it should be more straightforward like this.
It
Like,
will be-
obviously, like the total and then what you're picking out of.
Yeah.
instead of
It will
what I
be
just said.
much more like the homeworks that we did on these, like with the nurses and the like the test questions, and she like knows 5 of them. What's the chance all 5 of those show up on the 6-question test? You remember those questions, right?
Mhm.
no, let's see.
No?
So
You got it in your homework somewhere.
Okay.
You can go back and take a look, but they're just gonna look like this.
Okay.
They'll look like those.
Yeah, because I feel like a lot of the things I can like, okay, if it's like laid out, find this thing with these things.
Yeah.
It's pretty simple, but I just need to get past like setting up.
Mm-hmm.
I'm also worried about that
Like,
too.
Yeah, reading the question is it is certainly an acquired skill, especially if it's reading the question and interpreting the question, right? So
Do you have any tips for that?
I certainly do. I most certainly do. My overall general tips for understanding a question, these are the story ones, right? Because like true or false, there's only so much you can do with true or false, right? Like you either know it or you don't. Try to parse out for words that are like always or never, because those ones are usually hints that like there might be an exception. So carefully consider that. But it's like, one second. So like, let's think about this for a second. Like, actually, not sure. Let's just say hypothetically we get a question that looks like, I'll just pull up the homework really quick. Let me see really quick. If I go here and I switch scenes to that one. Excellent. Wonderful. Okay. Oh, this is the homework, yeah. That's the test, but let me just recompile this and that will go away. Don't look too carefully at that, everybody. I mean, hey, I told y'all to come to the review, right? Let's just say, for example, I had a problem that looked like, there's probability combinatorics, conditional probability. Let's just say I have a problem that looks like this number 3 problem right here. It's a little difficult to read for you guys because it's blurry, but I will read it to you and you'll hopefully remember what the problem said. And then I'm just going to go back to my
You said
notebook
number
anyway.
3?
Yeah, this number 3 here from homework 3. And in fact, let me switch back to my tablet scene here because I actually have the answer key from the homeworks and I can just pull it up here, right? Let's go back to homework 3. And let me just show you how I would work out this problem, right? And in fact, I'll even give you this one, because this one is a little bit confusing, right? Let me just take this whole thing. We're going to do question 5 from that homework, actually. And we're just going to look at it, and I'm going to tell you about how I would do it. You can read that, hopefully. Okay? Here's the notes that I left in the answer key, but I'm going to give you exactly what I would have written now. I just want to make sure that I do it right, so I'm going to take this and make it small and put it up in the corner, right? Okay. So I see a problem, and the steps I would give you are first, just give it a read, see if you understand what it's asking. Just general form, give it a skim. Once you decide you're ready to, like when I'm taking a test, if I find a question I don't know how to do or that's going to take me like an inordinate amount of time to understand and work through, I usually come back to that one later. Because when I take tests, I like to blow through the ones I can knock out quickly. I just go through and right? So if I have to come back to this one, the first thing that I'm going to do is I'm just going to write down everything the problem gives me, right? A student prepares for an exam by studying a list of 10 problems. 10 problems. She can solve 6 of them. 6 solvable. For the exam, the instructor selects 5 problems at random from the 10 on the list given to the students. So I have, 5 on test. What is the probability that the student can solve all 5 problems on the exam? Okay.
Can we have a second to try to set it up on our paper?
Sure, go ahead. Go ahead and try to set it up. And if you're at home as well, go ahead. Absolutely try and set it up. I don't see any questions in the chat, so In the meantime, if you've got one, throw it in there and we can do it next. Actually, it looks like there's one person viewing, but I don't know if that's just me currently viewing it.
Oh.
I actually don't really have any way to tell. I don't think it's me though, so. Hopefully. We'll see how it goes. It's up to 3 views though, so 3 people have opened it, or 1 person has opened it 3 times, or some combination of that, right? Some combination. What are the different ways? How many? Pretty sure that's 6 as well.
Yeah.
Because you could have. No, it's 4 actually. It's 4, because you could have 1 person do all 3. You could have 2 people do 1 and 1 person do. Wait, no. Yeah, I'm pretty sure it's 4 though. There's some formula there. So the first thing that I do when I'm looking at this kind of problem, and I'm sure that you're still working on it, and that's fine, but the first thing that I've figured out is that if this is a probability problem and we're picking something from a list of, things, this is going to be one of those combinatorics problems that has this formula, right? That has like this format right here, right? This is what I've figured out. Right? Because she's asking, what's the probability this student can solve all 5 problems that end up on the exam? Did you all get this far?
Yeah.
Excellent. What did you put on the bottom?
10 over 5.
10 over 5. 10 pick 5. Why 10 pick 5?
Because the total is 10, and then she's going to have 5 out of those. On
Yeah.
the test.
5 on the test, absolutely. So 10 Qs, 5 on test. What that is that represents every single possible test that could be picked and given to the students, right? 10 pick 5 is the number of unique ways you could receive this test and have to take it, right? Does that make sense?
Yeah.
Okay. What's on the top? What did you put?
Well,
No, go ahead.
okay, well,
Rachel,
I
Alec?
am not sure about it, but
Sure.
I think that I put on the top of the left,
Mm-hmm.
of the 5 problems she picked, 5 of them I could do, and of the 5 problems she didn't pick, 1 of them I could do.
Okay.
But I don't know.
5, 5, 5, 1. So that doesn't work with 10, 5 on the bottom.
But I did 10, 6.
But you did 10, 6 on the bottom. So let's branch this off then. We have over here, this is the Rachel method. And over here, let's write the Alec method, okay? Let me copy this and then we'll adjust it to yours. Hopefully, they should actually pan out to be the same thing.
Oh, that's great.
I think they will. 10 questions, 6 solvable. And Alec on the top put 5 questions, 5 solvable. And in fact, what he did is he did 5 on test. Right?
Is the purpose you just have to account for everything on the top that you've thought about in that way on the bottom?
Yeah, exactly. You need to keep them parallel.
You need to keep, for example, a questions type thing, whether it's on or off, and then like solvable on the bottom.
Yeah, if you put solvable on the bottom in the denominator, it's got to stay on the bottom in the numerator, right? Now the Rachel method, I'm going to assume you did 6, 5, 4, 0, right? Because what she did is she said 6 questions that were solvable, pick 5 on test, 4 unsolvable questions, pick 0 on test. Now you got to notice as well, the top is what changes. That changes, the classification, because this is exactly the outcome that you need. You need 6 of the ones that you can solve, 5 of those need to go on the test. 4 of the ones you can't solve, you need none of those to go on the test. Of the 10 questions, where 5 of them will end up on the test. Like this denominators, or the bottoms of the picks don't change, but the tops do. Solvable, unsolvable Qs, on test, on test, on test. On test, off test Qs, solvable, 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 right? Now, hopefully, either one of these will work. Does anybody have any numbers that they got? Well, I can tell you really quickly. Yeah, let me just give myself some space to work with here.
I got 5/210.
5 over 210? That'll be something. So Rachel's will turn into 6 pick 5 is 6 over 1. So that's 6 times, how many ways are there to pick 0 questions from a set of 4? There's only one. This will be 6 times 1 over 10 pick 5. 10 pick 5 is going to be 6 times 7 times 8 times 9 times 10 over 1 times 2 times 3 times 4 times 5, right? But the easier way to write it for me on here is actually just 10 factorial over 5 factorial, 5 factorial. 252. So she gets 6 over 252. And Alex should get, well, 5 pick 5 is 1. There's only one way to pick a set of 5 if you don't care about order. So that's 1. And then 5 pick 1, well, hopefully you got a number that makes sense, but that's 5 factorial over 1 factorial, 4 factorial. That should be 5. Exactly. Over 10 pick 6, that's 10 factorial over 6 factorial, 4 factorial, which gives me 210. Are these numbers the same number? 6 over 252, 5 over 210. Calculate. That's the same number.
Nice.
Dope. So as you can see, as long as you keep consistent what you have on the bottom, right, and you switch the groups appropriately on the top, you'll get the same answer whichever way you choose to assign the groups. Just remember, logically, this bottom represents all of the possible outcomes, your 100%, if you will. And on the top, you need to set it up so you're getting a specific scenario. The top 2 numbers should add up to the bottom number, and they should switch groups. The bottom 2 numbers should add up to the bottom and be classified the same way, right? Now you'll notice I did a lot of writing here. Like, when you actually do the math, do you need to write these words here? Absolutely not. Would I recommend it? I absolutely would, because then you're pretty much guaranteed to not get confused, right? You'll at least know what you were thinking when you were writing the problem the first time. So, in terms of like, this, by the way, is equivalent to 1 over 42. So we got the right answer, which is super nice. But basically, if you see a problem and you're not immediately sure of what to do, which some of these you will just be immediately sure because you know them, right? The other ones that you have to think about a little bit more, write everything out, start trying. The first thing is just write down everything the problem gives you. And then the second thing is just try stuff and take notes of what you're trying. And if it makes sense, just keep going, right? For a question like this, that's really all that you can do is just try stuff that makes sense. But the writing down everything that you get from the problem is going to make it more clear like what it might ask you. Because maybe you read this question, you're like, I'm not 100% sure like what it actually wants me to do. Like I don't 100% know that it wants me to do something like this. Well, if I write this down, then maybe I can start to get a sense of like, what do I have to play with? Like what, because the question that we give you on a test is never actually going to ask you to do something that you can't do with the information that we've given you, right? So seeing the information laid out like this can sort of help your brain recognize patterns, things that you have, and like maybe something clicks, right? I'm sure we'll do more examples from this later as we continue to answer questions. I might pull more stuff from the homework and go through again, how would I break down this problem? But I think that's probably everything we need for combinatorics. This is pretty much everything. So who's got another question? That was Spencer's. What about other Spencer? I mean, Spencer, the other Spencer was actually the first one to show up, so I think you're other Spencer today, actually. So that was other Spencer's question. What about What about True Spencer's questions, if he's got any?
True Spencer. I have kind of a weirder one.
Sure.
The biggest problem I've had with my homework
Mm-hmm.
is my fat fingers screwing up on the calculator all the time.
Yeah.
I don't know how, but especially when it comes to the expected value of something, and you get those long strings of numbers.
Yeah.
I will enter like the same thing 3 times and get 3 different answers.
There you go.
Do you have any like, I don't know, good test practice tips or calculator?
Yeah, did you
suggestions to make sure that we can get the right answer?
Yeah, so if you've got some big long string of things you need to calculate, right? Like maybe let's say we have something like -2 over square root 5 times square root 10. Or like if we go back to like the big expected values one, it's like 0 times 0.3 plus 1 times, and even like the squared versions, right? 1 squared times 0.15 plus 2 squared times, like an expected value of x squared here, right, is what we're doing. Like an e of x squared. 2 times, I don't know, I gotta do some math in my head, 0.5, and then that's what, and then like plus 3 squared times 0.05, right? Like these are both examples of places where like missing one button on your calculator is gonna be obnoxious. And you have this huge string of stuff to put into your calculator that's also obnoxious. And you guys don't have the luxury of a calculator that looks like this, which is a shame, but a necessary evil. So what are my tips? My tip is to do one calculation at a time. So on this bottom one, that's really easy, right? Do everything you can do in your head first. So my first step is, before even touching the calculator, cancel that. Turn that into 0.15. Cancel that. Turn this into 0.15 because it's 1 times 0.15. Turn this into 4 times a half. And if you need to do that on the calculator, you can write 4 times 0.5. But hopefully you can look at that and go, oh, it's 2, right? Even if you have to write it out. And then 3 squared times 0.05. 3 squared is 9. And I don't know what 1/20th of 9 is. I mean, this is literally just 9/20ths, but if I didn't know that, right? My suggestion is get to this stage. And then after that, in the calculator, I would do this, right? So now all this red stuff I've done by hand, and then I'd move to the green stuff, which is 9 times 0.05 in the calculator. Not, what a surprise. 0.45. And then in the calculator, I would do 0.15 plus 2 plus 0.45. Now, this is simple enough that you could honestly do this entire expected value in your head. Just because I was coming up with it off the top of my head, right? Like, you could do this all as mental math. This one is like obnoxious to do as mental math, but it's fine. It's doable, right? And then you add that up. 0.15 plus 0.45 is 0.6, so this becomes 2.6, right? But in terms of like, what the fetch do I do with this? Well, the first thing I would do is, if I have a calculator, what I would do is I would do first, what is square root 5 times square root 10? Equals, let's call it Q. And then in the calculator, I would type -2 divided by Q, right? So just break it down. It gives you less room for error. And also, write down everything you're doing, right? When I grade your tests, like, I will be able to tell if you've just made a calculator error. It's very easy to tell on the homework, especially because a lot of you do good jobs of writing out your work, and I see that you've added something like 1.2 and 2.4 and gotten something that starts with a 6, which just tells me, something has gone wrong. This is not, and usually that's, if on the test it occurs, it's only 1 point off. And I'd love to say that it's no points off because you know how to do it, but in the real world, you also do have to get the right answer, so we balance that. But the basic tip that I have is break it down into more steps. And write it down. Write down the number that you get, and then if you're really worried, just double check it. And if you get something different from what you wrote down the first time, do it again and again and again, and just be really, really careful. Hopefully that won't be too much of a problem for you, but breaking it down into smaller pieces that are simpler to type into the calculator is always going to help you. Unless you do some mental math wrong. If you write 3 squared is equal to 8, that'll be a point off, right? And I will, after I see an algebra error, when I'm grading the test, if you've written all your work out, if I see a calculator error or an algebra error, I will go through the rest of the question as if that were the correct number. And if you did everything correctly with the wrong number, I write the following. I write WNRS, which stands for wrong numbers, right steps. So you only lose the 1 point. Or if like the part A had a calculation that you have to use in part B, you'll lose a point on part A, but then on part B, I will probably write WNRS, right? So not too much to worry about, but just be extra cautious if you're worried about it. All right? Does that covers everything you need?
Yeah, very helpful.
Solid. Rachel, Alec, either of you got anything we want to talk about?
Mine's kind of a long question, so I feel really bad asking it.
Not allowed to feel bad. This is the review.
Okay, so for homework number 4, when you do the tree things, I feel like I can write it out, but somewhere in the steps, something's like not
The
quite
tree
what you
things. Let's do the tree things. Absolutely. I wrote a tree question for the final this last term that I don't think, like I tried really hard to write it really clearly, but I think it was just too long and it didn't. It was about a hypothetical Monty Hall parody. You guys know the Monty Hall paradox? No? Okay, well, maybe I'll save it for later then.
Maybe that's why it was confusing.
Maybe part of the reason that this event tree was confusing for you is you may have given too much weight to the fact that it was given on the conditional probabilities homework. Actually, let's do this 7 one because I haven't already drawn the tree, right? Let's copy that one over. Okay. This may be too small for you to read if I shrink it down, and that's going to be okay. But it's okay. I should have enough space to do this, right? How do we draw an event tree, and how do we make sure that it's actually like accurate, right?
And then how do you label? Because I watched your other review,
Mhm.
and when you put it with the percentage, it makes more sense to me of like
Yeah.
the steps. But when you put it into like the other notation of just
Like the actual
the
probability of? Yeah,
then
okay.
I get kinda lost.
We'll get there. Let's break down this problem how I would break down a test question. All right, first thing I'm going to do is just read it. The purchase website for a smartphone includes an ad for a case. If phone customers click on the ad, they get more info about the case, and they have the option to purchase the case along with the phone. The website host records the following data about visitors to the website. 40% click on the ad. So 40% click. That's the first thing I'm writing down. 80% of these make some purchase. So 80% of clickers, right, buy. Half purchase just the phone and not the case, while the other half purchase both the case and the phone. And nobody does just the case without the phone. So 80% of clickers buy. Half of these, right? Half the 80% by both, half the 80%, and this is of course the 80% of 40%, right? So half the 80% by phone, okay? The remaining 20% of these customers is still the clickers, right? The remaining 20% of these customers leave the website without making any purchase at all. So 20% of clickers don't buy. Of the customers who do not click the ad, which is 60% of them, right? 60% don't click. 70% purchase a phone. None of them can get the case because they didn't click the ad, right? So 70% of no clicks buy a phone. And then 30% don't buy. 30% of no clicks, right? Don't buy. Use this information to answer the following, or state that there's not enough information provided. The hint is that we will probably never give you a question that does not have enough information to answer it. So A says, what fraction of visitors to the phone website ultimately purchase at least a phone? Right? So that's the phone and the case, or just the phone. So we want to know, if it's a fraction of visitors, that means it's also going to be a percentage, right? Or like a probability. What's the probability someone comes to the website and buys at least a phone? That's another way I would interpret that. So I would write A as the probability that they, and let's just call B buying a phone. In fact, let's just call it P phone. Probability somebody comes to the website and buys a phone. Flat, right? And then B says what? Of those who do purchase a phone, what fraction of them at least click on the ad, and what fraction of the buyers get the case, right? So B is asking us what? Well, it says we're only going to look at the people who bought a phone. And so that should put off alarm bells in your head. We have a new 100%. And that means this is a conditional probability, right? So we want to know the probability, given that someone has already purchased a phone, of what? The probability that they click, given that they bought a phone. And we want to know the probability that they have the case, given that they bought the phone. Okay? That's everything from this question, right? We have broken down everything written in this problem. It is now written in a format that is more organized and easier to access for us. And now we can start to build our little tree. I'm going to delete this because the problem is huge. This is another problem that people can run into. Like, they see just an enormous problem and they just, it can be a little bit overwhelming, right? So break it down like this. This is way easier, right? In fact, I love being able to move this stuff around. It's so nice. Let's just write it like this, right? Let's draw a tree. We have 100% of people that are coming to the website. That is where we're going to start. We draw a little guy, right? Little person. And we know that that person has two options. They're going to see an ad, and they can choose to either click it or not click it, right? So let's draw that branch first. Click, no click. Is that right? That is right, yes. So we have 40% of people click. I'm going to turn that into 0.4, right? And we have 60% of people who don't click. I'm going to call that 0.6, okay? Now, of the clickers, 80% of them will buy, and 20% of them will not buy. So let's make that the next branch. And hopefully we can also make that a branch over here, right? You want to make the same level of branch represent the same thing on all the branches, if you can, right? Hopefully that's something you can do. And it does happen to be something we can do here, right? We know 80% of clickers buy and 20% don't. 70% of no clickers buy and 30% of them don't. So let's add this branch onto the tree. This will be buy something, right? Buy or no buy. And let me just take that and copy it. And then let's take this and move it down a little bit. Now we don't have any more branches for the no clickers. They're done. But there is one more branch for the clickers who buy, right? Half of them get both the case and the phone, and half of them only get the phone. So on this click buy branch, I'm going to add another one. We don't know anything else about these guys because we know they don't get the case, right? And this is like the case branch, right? So the buyers over here, I didn't even finish filling in this branch, but the buyers who clicked are 0.8, and the no buyers who clicked are 0.2, right? 0.2 of this 0.4. Does that make sense? Absolutely. Okay. And then down here it was 0.7 and 0.3. Now we have one more branch like we were talking about. It's the case branch. We have case, no case. And that's just going to be 0.5 and 0.5. Half and half. Okay, the first thing we need to do is answer question A, right? The question A says, what is the probability? Let me just make this smaller really quick. Move this over here. Take that right there. Question A says, what is the probability that somebody buys a phone? So let's go to the ends of all the branches where somebody buys a phone. We know if they're on a buy branch, they have purchased a phone, right? So I can look at this and say all of the people at these ends bought a phone, so I'll just look at this branch. Or I can go down all of these branches, right, and add them up. This would just save a step, but for the sake of being as explicit as possible, let's do it. Let's go to every single endpoint where somebody bought the phone, multiply the probabilities down the branches, and add them up. And it's actually just these ones. I drew an extra branch there. So the first branch where somebody buys a phone is when they click, they buy something, and they buy the phone and the case. That is the probability that they click, buy, and have the case. It's 0.4 times 0.8 times 0.5, right? That's just a probability of intersects, okay? So we have 0.4 times 0.8 times 0.5 plus, because we're just going to add these together. Now we want to know about the people who click, buy a phone, but don't get the case. That is an identical number. 0.4 times 0.8 times 0.5 plus. We're not going to look at the guys who don't buy a case even when they click. Because again, we're only looking at the probability that someone buys a phone. And these guys did not buy, right? So of the no clickers who bought, here's an endpoint where they do buy the phone, right? So that would be 0.6 times 0.7. And then for the last endpoint, the no clickers, no buyers do not buy a phone. So we're not worried about them. This is going to be the answer to part A. So let's break it down. Before I even touch the calculator, one thing I recognize is that this is half of a number and this is the other half of the same number. So am I going to type this into my calculator? Personally, no. You can if you want to, but I recognize that this is 1/2 of 0.4 times 0.8 plus the other half of 0.4 times 0.8. So I'm going to just turn that into 0.4 times 0.8 plus 0.6 times 0.7. Now the other thing I've recognized is that I know how to multiply decimals. And if you don't know how to multiply decimals, that's okay. I can come to my calculator now and I can type in 0.4 times 0.8. That's going to give me 0.32. And then I'm going to type in 0.6 times 0.7, and that's going to give me 0.42, and I'm still adding them up. This I can do in my head, right? Or I can even just do it like this, right? 32 plus 42, 4, 7. This is going to be equal to 0.74. What does this mean? Well, the answer to question A was what was the probability that someone who visits the website buys a phone? It's 74%. That's the answer to part A. Did we get it right? Sure looks like we did. This is making sense, right? Okay. Now, let's take this and make it smaller, right? That's not what I wanted. I wanted that. Let's go ahead and make that small, put it up here, because we did it already. Now the question is, what is the probability, if you know that somebody bought a phone, what's the probability that they clicked?
I have a question.
Hit me.
How come, so why do we multiply them together? What's the intuition behind that?
The intuition of it is if we're looking at 100% of people who visit the website, let's say that there's 100 people who visit the website,
Okay.
right? If I have 100 people who visit the website, I go down the first branch. Let's say I want to know what's the probability that somebody clicked but didn't buy. Clicked on my ad, but they didn't buy anything, right? So of these 100 people, this number right here tells me 40% of those people clicked on the ad, right? And so how many people clicked on the ad?
40.
40 of them. 40 clicks, 40 clickers. And then the question is, of the clickers, how many of them didn't buy anything? Well, the percent is 20%, right? Because right here, I notice I have something that adds up to 1, right? 0.8 plus 0.2 is 1. This is representing all of the people who clicked, right? So, of the people who clicked, how many did not buy? 20%. What's 20% of 40? Well, 10% of 40 is 4, so 20% of 40 is 8. So we have 8 clicker no buyers. This is the probability that you clicked and did not buy. The reason that we multiply those together is because of the MN rule, which it's not really that useful to know the name of, but it's just like I'm doing 20% of 40%, so I need to multiply 0.4 times 0.2, right? Yeah. It's just, yeah, I think it's MN rule is what we would call that. But honestly, I don't think it's that helpful to name because it makes more sense to me to think about it like when I draw this tree, this branch right here represents 20% of the 40% of 100%. And so I can take the first 40% and then take 20% of that just by multiplying them together. So yeah, let's break this down into the conditional probability. So the first thing we need to recognize is we're looking at a new 100%, right? We know that the probability that someone buys a phone is 74%, right? 0.74. So if I had 100 people come into the store, how many of those people am I looking at now? Only 74 of them, right? Which 74? The ones that bought a phone, exactly. So no matter what happens here, I know I'm going to have on my denominator a 0.74, right? I'm only looking at the 74% of people in my new 100%, i.e. the people who bought a phone. But what goes on top? Let me remind you of a very useful formula here. The probability of A given B is, of course, equal to the probability of A intersect B over the probability of B. So in this case, the probability of a person having clicked, given that they bought a phone, is equal to the probability that they were both a clicker and a buyer of a phone over the probability that they were a buyer of phones, right? And that's pretty easy. Which branch here is the intersection of clickers and buyers? It's this branch, it's these two branches, right? These two endpoints, but really it's just click buy right here. That's going to be 0.4 times 0.8, right? And we know from up here what 0.4 times 0.8 is. That's 0.32. So all I have to do now is say that is equal to 0.32 over 0.74, which is equal to 0.432432 repeated. Or, if we want to do this in fractions, 32 over 74, 16/37. So, of those 74 people, and in fact, not even that. So, if I know that you bought a phone, I know that there's about a 43% chance that you also were someone who clicked the ad. Does that make sense? Yes, no, maybe so. Does this help you see like how we build this?
Yeah, the only thing I'm
Yeah.
a little bit confused by is, so the probability that it's clicker intersect buyer, that's 0.4 times 0.8?
Yeah. That's click branch times of the clickers, how many of them bought, right? Just like from up here.
Okay, yeah, that makes sense.
Okay. Absolutely. Hopefully you can see what the probability that someone bought a case, given that they bought a phone, would be. It's just instead of doing both of these branches and including the people who didn't buy a case, we're now going to follow this branch only up the top branch to the people who bought a case and bought a phone and clicked on the ad, which is just going to be half as big as this one because this is half as big. It makes up half of this endpoint, which is what we used before, right?
Which would also be the same as 0.4 times 0.8 times 0.5 over 0.8.
Exactly. It'd be exactly the same thing. Yeah. Does that make sense? Does that track? Let me just write it out for full clarity. The probability of someone having bought a case if I know that they bought the phone. And actually, let me make this a little bit more clear as I write this out. How many of the people on this tree bought a phone? Well, these guys bought a phone, these guys bought a phone, and these guys bought a phone. So I want to know what fraction, if I take, all of my phone buyers, which is all the red branches here, all of them are phone buyers. I want to know what fraction of those people are made up just by the blue branch, the people who clicked and bought and had a case. And hopefully you can see that this number, this fraction of people on this branch, is going to be a minority at the very least, right? Because first of all, the people who don't click but buy outnumber the people who click and buy. Because 0.6 times 0.7 is bigger than 0.4 times 0.8, right? So then we're having that, we have that, and then we're going to half it. So maybe that's a different way to intuitively think about this question, but mathematically it's just 0.4 times 0.8 times 0.5 over these numbers from the beginning of the problem. Out of the total of all the branches where people bought phones, if that makes sense. So it's like, yeah, here's the branch, right? Here's the branch we're interested in. Here's all of the branches where people bought a phone. Make sense? Easy peasy. Don't get confused by this conditional thing. All it's saying is look at a more narrow set of people, or look at a more narrow set of outcomes. Give yourself a new, smaller 100%. Easy peasy, right? Had everything we wanted on event trees. Yes, no, maybe so. Excellent. Okay.
Yeah, Drew, go ahead.
Okay.
I was just going to say, kind of going along with that,
Mm-hmm.
I guess where I'm hung up on that intersect definition is that I thought the probability of the intersect only equals the probabilities time each other if they're independent. Are we saying these are independent factors in this way?
Let's go back to my whiteboard for independence really quick. It's going to be a bit of a slide, but we're going to get there. In fact, let me just, oh wait, oh no, that's the conditional version. I was about to be like, yo, I'm goated. Give me one sec. Let's pull that up really quick. Where do we find that? There it is. The probability of A intersect B is equal to the probability of A times the probability of B if they are independent.
Right.
So isn't that just because the Bayes rule was the
Mhm.
probability of A intersect B over probability of A times probability of B? Wasn't it only if that equals 1?
Only if something equals 1. I'm not sure.
Because if you divide both sides by probability of A times the probability of B, then it's the Bayes rule equals 1.
Well, because Bayes' theorem is the conditional one, right?
Okay.
Are you saying do this over P of A times P of B? Would have to be equal to 1? I mean, that's true, but also doesn't really help you with the intuition. Basically what it comes down to is once you've written out an event tree, they don't have to be independent for you to follow the tree, right? So these events are probably not independent just by how they're drawn. It seems pretty clear that if I tell you somebody bought a phone, it probably gives you more information on whether or not they clicked to the ad, right? But if you can write it out like this, just strictly speaking, the probability that someone is both a clicker and a buyer is this branch. Like, that's just how we've written it. So, yeah. Actually, you want to know what it is? The reason that this is equivalent without being independent is that this right here is the probability of click, and this right here is the probability of buy given click.
Okay.
Exactly. And if you were to Bayes all that out, you would find out these are equal.
And that's how I've been writing it.
Yeah.
Okay.
So glad we parsed our way out of that one.
Okay.
Makes sense, right? That's why we include these event trees in the conditional probability, like, lecture, is because, this branch right here is even like the probability that you bought a case given that you have bought a phone and clicked, right?
It's like double given, right?
Uh,
It's also given that you clicked or something.
Well, I mean, this one doesn't have to be a double given because we'll have to solve for that. You can really never have a double given because that would imply two 100%. But in the building of this event tree, this is a new 100% right here, right? But we're basing it off of our calculations from this 100%, which were coming from our calculations off of this 100%, right? Every branch is a new 100%, so it's a new condition. But, you would probably write it more like this, right? Because this is equal to probability of click times the probability of buy given click.
Oh yeah, because you can also write that as probability click times probability by given click. Yeah.
Yep.
Okay.
And then that will put probability of click on the bottom. They'll cancel, and it will be the probability of buy intersect click. Super cool stuff. Fun new stuff to think about, new ways, right? That covers probably everything from event trees. I haven't heard any questions yet on like expected value, variance, correlation, stuff like that. So maybe those ones are a little bit more clear, or we just haven't gotten to those questions yet.
Question.
Okay, random question.
When you separate out variance
Uh-huh.
and you take something out, then you have to square it.
Yes,
But when you do it for covariance, you don't.
exactly. Absolutely correct.
When do you not do, when you're separating everything, when do you not do two covariance of whatever?
Okay, let's talk about that. If I have the variance of y, we know the formula for that. It's e of y squared minus the squared e of y, right? So let's make it a little bit more complicated. What about the variance of 6y plus 12? Question mark. Well, if I'm following my little algorithm, the first thing that I'm going to do is I'm going to split it at the pluses and minuses, right? So I'm going to have the variance of 6y plus the variance of 12. And technically, because I am passing through a variance operator, I should have covariances between each of these terms that I break apart. So pretty much always. But hopefully you can see I'm going to have two covariances, because I have this direction of covariance and I have this direction of covariance, right? This two covariance thing, what it's accounting for is actually the middle term in this squared from the expected value, right? That two covariant, because like if I did 6y plus 12 squared, that would give me 36y squared plus 6 times 12 times 2 is what? 6 times 12 is 72. Yeah, it's 144 plus 144y plus 144, right? And then if I took the variance of that by spreading everything through, I'd pull out this 144. I'd pull out this 36, but I'd still have the y squared to deal with. And so, well, this would be an expected value thing, but it's a whole thing, right? These two covariances are accounting for the OI in FOIL. No. Yeah, the OI in FOIL.
The inside.
Yeah, the outside and the
So
inside.
these two-
So this would be two covariants of 6y and 12, right?
Which is 0.
But it's 0 because 12 is a constant. So it can't covary, it also can't vary. And then I'm just left with the variance of 6y. And then the second step in the algorithm is pull out a constant, and if it's a variance, square it. So that gives me 36 variance of y. Easy peasy. Even if you add 12. Because the thing is, variance is trying to measure how far off the line you're going to be. And if you just straight up add 12 to every observation, you're not going to do anything except shift both the line and every dot up by 12.
Yeah, that makes sense.
It's not going to affect variance at all.
And then if it were 3 variables, you'd have to do it so like each one.
Yeah, so let's think about this, right? Like I only had one variable there, so it ended up I'm only looking at the variance of one variable. But let's talk about like, what if I wanted to do the variance of something like 6x minus 4y plus 19 or something like that, right? Well, the first thing that I do always is I'm going to split it at the pluses and minuses, right? Variance of 6x plus the variance of negative 4y plus the variance of 19. And then for variance, I'm going to give a covariance term between each of these things, right? Each set of two of these things, right? So it's kind of like a 3-pick 2. How many covariance terms am I going to have? 3-pick 2 is just 3, right? Because it's 1 times 2 times 3 over 1 times 2 times 1, right? 3 factorial over 2 factorial, 1 factorial. So I'll need to add 2 covariances between these first two terms, 6x and negative 4y. 6x, negative 4y. Then I need to add 2 covariance terms between the first and the last, so that's 6x and 19. And then add 2 covariance terms from the final 2 terms, which would be negative 4y and 19. But again, the nice thing here is the ones with constants are going to cancel because they can't vary. So then I'm just left with this variance of 6x plus the variance of negative 4y plus 2 covariance of 6x and negative 4y.
Which is 36 variance of x plus 6
Yep.
variance of y.
We're going to pull up.
Is it 48 variance of, or negative 48 covariance of x, y?
It would be, yeah, negative 48. We're going to pull everything out of the variance. The one thing I want to show you, though, this is the intuition behind why you pull stuff squared out of variance. Let me rewrite this in a way as the covariance of 6x and 6x. Pretty cool. Plus the covariance of negative 4y and negative 4y plus 2 times the covariance of 6x and negative 4y. And then let me do this really quick. Does that look like anything to you? Because to me it looks like a foil. Right? Variance is a squared thing, right? It's a squared term. If the two things are independent, this goes away because they don't move together. And then we only have to look at the ways they move with each other, like with themselves. By the way, this is not an insight you're expected to have the first time you go through this class. I'm TAing this the 4th time now, and this is the first time I've seen this. So, covariance of 6x and 6x. I can pull out a 6, I can pull out a 6. That's 36 covariance of x and x, or 36 variance of x, right? Same thing over here. For this covariance, I'm going to pull out a 6, pull out a negative 4. Multiply them by 2. 6 times 4 is 24. That gives me 24 times 2, which is 48. And then I've also made it negative. Because again, covariance is allowed to be negative, right? So that's minus 48 covariance of x and y. And then this is going to be, I pull out a negative 4, pull out a negative 4. That's negative 4 times negative 4, which is positive 16, right? Plus 16 covariance of y and y, or variance of y. Make sense? That's the most in-depth review and explanation of passing variance operators through I have ever given. So,
Wait, can I ask one question?
yeah, hit me.
So I didn't understand that part about independence, like if they don't vary each other's.
Yeah, so if x and y are independent, then strictly speaking, they don't correlate with each other,
Yeah.
right?
Okay.
And so if they don't, it's because they don't covary. Because basically what it comes down to is your covariance of x and y is equal to the expected value of x times y minus the expected value of x times the expected value of y. And that should look fairly familiar as well. What the heck is that? If I go back a couple pages and we take a look at one of our independence noteboards, that sure does look familiar. A intersect B, A times B. Well, we've got X intersect Y, X times Y, right? And if this is 0, then that means the expected value of X times Y is equal to the expected value of X times the expected value of Y, right? And if that's the case, they're independent, based on that first independence thing that we saw, right? Because this is asking for a specific value of x and a specific value of y, right? If I multiply them together, do I always expect that to be the same as that average of x and y together? Make sense?
So if correlation is 0, they're independent, right?
Not necessarily.
Oh.
If covariant-
Independent, then correlation is 0.
Yeah, if they are independent, correlation is 0. I'm going to be real with you. I can't think of a case where you have a 0 correlation and they're not independent.
But it
Like,
could
in
happen.
my head, that doesn't make sense, but there are some technical, statistical, like, places in which that exists, I assume.
Probably
Okay.
not the test.
Not, definitely not on the test. Absolutely not. Love the good notes usage, by the way. I can give you this
Oh.
color scheme if you want.
Yes,
Um,
please.
It's the same color scheme that's on teamwork.org. So,
I've learned how to use like the laser, like you're doing it, like, oh my goodness.
yeah, it's nice.
Got all these techniques.
I have a question.
Hit me.
When we're done with this, can we do problem number 2 on homework number 7?
Problem number 2 on homework number 7. I think we can make that happen. Huh?
I agree.
All right. Problem number 2 on homework number 7 is a popular question. Okay. Okay, you guys. You guys, this one's going to be easy peasy for you now. Come on. Nah, I'm just kidding.
I mean, it was pretty late, so
That's fine.
it could just be one of those red-eye homeworks. But I just think it'd be cool to see it done.
This is a pretty nice problem, because as I'm reading this problem, I realize, oh, they've gone ahead and written everything out for me already. Assume that y1, y2, and y3 are random variables with these expected values and covariances. The nice thing is they've given me every expected value, they've given me every variance, and they've given me every set of covariances, right? They've given me y1 to 2, y1 to 3, and y2 to 3, because order and covariance doesn't matter, right? And they just want me to pass an E operator and a V operator through. Super nice.
Oh yeah, that's what we just did.
Yeah, that's what we just did. But let's do it again, really quick, because we haven't done it with 3 variables yet. Now, just really quick, for the sake of making my life nice, I'm going to say y1 is equal to A, y2 is equal to B, and y3 is equal to C, because I don't want to have to write all those subscripts. You'll have to bear with me on that one. So, expected value of 3A plus 4B minus 6C. What's the first step?
Separate them at
S-
the plus minus.
Split them at the pluses and minuses. Expected value of 3A plus the expected value of 4B plus the expected value of negative 6C, right? What's the next step? Anybody? Next step?
Pull out the constants.
Pull out the constants. Do I need to square them?
No, sir.
No, sir. These are not variance terms. 3 times the expected value of A plus 4 times the expected value of B minus 6, because I've pulled out a negative 6, times the expected value of C, right? What's next?
Oh, you just plug it in.
I just plug in the numbers that I have, because I've gotten it down to numbers that I know now, right? So let's plug it in. 3 times expected value of A, expected value of y1 was 2, plus expected value of B was negative 1, so this is going to be 4 times negative 1, minus 6 times the expected value of C, or y3, which was 4. Then let's cycle back on our colors really quick. 3 times 2 is 6. 4 times negative 1 is negative 4. Negative 6 times 4 is negative 24. Right? 6 minus 4 is 2. 2 minus 24 is negative 22. Easy clap, right? Easy peasy. That'll cover that one. Let's do the variance one, okay? Variance of 3a plus 4b minus 6c is equal to, what's the first step?
So split it at the side.
Split it at the pluses and minuses. Variance of 3a plus variance of 4b plus variance of negative 6c. Anything?
You get 2 covariance of. Well, should have 2 covariances.
Yeah, absolutely. I need to get all of my covariances. So I need 2 covariances between each of these new sets of parentheses, right? So I need 2 of the covariance of 3a and 4b, 2 of 3a and negative 6c, and 2 of 4b and negative 6c, right? So plus 2 covariance of 3a, comma, 4b, plus 2 covariance of 4b and negative 6c, plus 2 covariance of 3a and negative 6c. Does that cover all my covariance terms? Yes, it does. I have 3 of these. I have that, and I have that. That's all the that's that I can have. So, what's the next step?
We want to make it so it's just like consolidate the variables.
Yep. Deal with all the constants, if you will.
Deal with the constants.
Right? Let's do variance of 3a turns into what?
9 variance.
9 variance of a. Right? Easy peasy. Pull it out and square it. Plus 16 variance of b. Pull it out and square it. Plus, or minus? Shouldn't that be a minus?
No, plus 36.
No! Variances are always positive, absolutely. Plus 36, variance of c. What do I do with these covariance terms?
You just multiply them. So it's like plus 24
Pull out all the constants.
covariance.
Absolutely. 3 times 4 times 2 is 24. So I get plus 24 covariance of a and b. 4 times negative 6 is negative 24, right? Times 2 is negative 48 minus 48 covariance of b and c. And then 3 times negative 6 is negative 18 times 2 is negative 36 minus 36 covariance of a and c. And then from there, plug in all the numbers and don't make algebra mistakes. Absolutely. I'm going to leave that one in that form because once you get it to here, you should be good to go. Okay, got it? Get these down to numbers you know. And then just plug in the numbers that you know. Anytime you see an equal sign, that's an opportunity for a substitution. Right? This is not like your education. These substitutions are equivalent. Right? A substitute teacher may not be. Kind of a far-reaching joke there, but we'll take it. Right? Mm-hmm. What else we got?
subject.
A different subject.
I was just wondering.
Yeah.
I guess there's going to be 5 true/false questions.
Are there going to be 5 true-false questions? Let's find out.
I was just wondering if those are.
Pretty sure there are.
Pretty conceptual.
Or if they're more just like math.
Yeah.
Yeah.
'Cause I feel like the ones from the homeworks, the true/false have been like.
Yeah, you gotta think about
Yeah.
stuff.
Pretty like, is this always true and stuff like that.
Hmm. One of them.
Yeah, there's a lot of those. Right, chapter or homework 7, and it's like bam, bam, bam.
Yeah, the true false are going to ask you about concepts, basically. You can do things like, you may, to check your understanding of the concept, want to pass through something like an expected value or a variance operator, right? Just to check, like, am I right in my intuition about this thing? Or like, if I pull out the constants and pass this through, is this actually true all the time, right? But for the most part, it's conceptual. In that, like, it's some rule for independence. Like, if they're independent, then this happens, right? And you need to know what is true if they are independent, and then see if you can get to the answer using, you know, math and stuff.
Independent but not correlated. They're correlated.
Yeah, or something like that. Like, maybe like the slope term beta 1 is 0 if and only if x and y are uncorrelated or something like that. That one I'd be like, oh, well, what's the formula for the slope term? It's either this or it's this. And I'd be like, okay, what are all the cases where that can be 0? Well, it can be 0 if this is 0, or if this is 0, or if this is 0, right? So if covariance is 0, then they're uncorrelated. So that's good, right? And if correlation is 0, then they're uncorrelated. And if standard deviation of y is 0, then actually correlation isn't defined, because that means that y is a constant. So that also works because they'd be uncorrelated, right? So in that case, I'd be like, oh, that's true, right? If I have the slope term equal to 0, they must be uncorrelated, which I believe was on the homework, this most recent homework. And more people put false than I would have liked. Though I will say, your guys' class has been making grading particularly easy for me so far. It has been quite nice. I don't want to say it's because you have access to summaries of every single lecture online, but it might be something like that. But also, like, you know, just a couple people just always have the correct answer, which is really nice. Like, I don't know, Megan just consistently gets, her homeworks look like my answer keys, and I'm just like, this is great, except this most recent homework where, I shouldn't actually tell you that, but she actually, I think, missed this question. I think this is the question, the beta 1. I don't know.
Told her how to do it.
It's all good. I shouldn't be telling you guys that, but you know what? She's fine.
She didn't believe it. Okay.
I'm recording this for everyone. It's okay.
You are on YouTube, right?
Yeah, we're gonna. Oh no! Put me up on live stream fails. It's all good. Apologies, Megan. Won't happen again.
Wait, which one was that? Did she mention the conceptual one?
I don't know. One of the true false, just one of the little ones, but it might have been this question that I just walked through or something else. It doesn't really.
So I guess
We don't need to talk about that anymore so much.
I guess some of those true or false ones,
Uh-huh.
like the equations can't help sometimes to help you think through it.
Always those equations. That's basically what they're asking you for, are formulas most of the time. Or do you know how to play with this? It's basically all the true false will ever ask you, which is pretty nice. We are running on close to an hour and a half. I don't have a real time to end, so I'll just keep going until you guys have questions. Or until you guys don't have questions, right?
Is there going to be like R squared stuff?
I can't remember.
I'm not sure.
But
I
if
mean, it
if
wasn't-
there is R squared stuff, we'll just be asking you to calculate it.
I guess it
and-
wasn't on the homework, was it? And it wasn't in the review.
There was one on the question in the homework where it asked you to predict height with weight and to predict weight with height. It asked you, if a person is one standard deviation taller than average, how many standard deviations heavier on average would you predict them to be? And the answer to that one was the correlation coefficient of 0.4, right? Because correlation is a measurement of the relationship in units of standard deviations.
Right.
And then the question right below that was what percent of variance in weight can be explained by variance in height? And that answer was rho squared.
Actually, can we do number 3?
Let's do number 3. Absolutely.
Then I'll be good to go.
Abso-frickin-lutely. I'm going to the wrong place. Abso-fwickin-lutely. Homework 8, number 3. Let's just go ahead. I'm not going to copy over the answers because I know them because I just graded this today. We'll just copy the question. Okay. In a certain demographic group, the average height for men is 68 inches. Average height, I'm going to call that height bar, but it could be like mu height or like mu h or something. In fact, let me just call it h bar. We're going to use bar for average soon in this class. We've been using it for complement, but basically if you're not doing set theory, if you're not doing like dartboards, the bar means average. Okay? So just keep that in mind. That'll be for the future. This is just how I'm going to denote it. Okay? H bar is 68 inches. I would also encourage you to label things. It makes life easier for me and for you because you don't get confused, and like it helps you know what these numbers actually mean, right? Average height for men is 68 inches with standard deviation 4 inches. So standard deviation of height is equal to 4 inches. The average weight is 185 pounds. Later, Spencer, thanks for coming.
Thank you very much.
Good luck on the test.
Thanks.
The average weight is 185 pounds. Olbs. With standard deviation, 25 pounds. Standard deviation of weight, 25 olbs. The correlation between height and weight is 0.4. Rho equal to 0.4. So question A, which is the only one that I copied, is predict how heavy a 72-inch tall person would be. So what is, this little hat means estimate, right? You're not going to see that on the test, but you'll see it more later. We'll start using these hats. Just know, what is the estimate for y given the estimates we're going to calculate for beta hat naught and beta hat 1 times 72 inches. And then it also asks, what is the predicted height? What is the predicted height of someone who weighs 200 pounds? And in fact, I'll do this y hat h, y hat w, or backwards. So one thing really quickly that I've done implicitly in writing it in this format is I have made a decision about what I'm going to use to predict what other thing, right? What is that? Well, it's going to be, for the first part of the question, I'm trying to predict weight using height, right?
So you essentially,
Mhm.
and this is the biggest part that I need, I guess.
Yeah, the biggest part.
Is the y is what you're looking for. And so you would plug in, for example, if y in this case was a weight, then you plug in a height and you're
Absolutely. The thing is, predict y based on or using x.
and then error is just
The-
that y equation, and then you subtract over the two things. So it's y minus
So error would be
like error
equal to y minus beta naught minus beta hat 1, or beta 1 x. Yeah.
Right. Okay.
Because that's literally just how far off of this line is the y value that you got.
Okay.
Because the line, right, is beta hat naught plus beta hat 1 x. This is slope-intercept form. This is a line. And then y hat is what you actually predicted. So if you take this number right here and you subtract that, it's saying how far was our guess off of the line. Later, Spencer. Good luck.
Cool.
And goodbye, Alec. Good luck.
Yeah, sorry, I gotta go.
No, you're good. Hope
Okay,
that
that's
covers
all.
everything.
Yeah, thanks for your help.
Yeah. Predict y with x, Alec.
Okay, I will.
Okay.
So you would just rearrange your like what is considered to be x, because you could never plug in like y to find the x.
Yeah, so you do have to recalculate a different beta hat naught and beta hat 1, a different a and b term based on what is y and
So
what
that
is
you can
x.
get a new, so you can use
Yeah.
x, which would be now 200 pounds instead of the height.
Exactly, because the formula for beta 1 is correlation times standard deviation of y over standard deviation of x, and if you flip what x and y are, you're going to get a different number. So just when you flip x and y, remember to recalculate beta 1, beta naught, or a and b, as you'll sometimes see it. I asked her to correct it and to make it beta naught and beta 1, but we had already sent the test in to be printed, so that was unfortunate. You got anything else you want to cover, Rachel, or are we good to go?
No, I think that's it.
Okay.
Thank you.
Good stuff. Well, that'll wrap up the review then. Thanks for watching, everybody who watched. It looks like we had one person who watched on and off 6 times, so that was pretty cool. We're going to end the review. Go ahead and end it here. Thanks for coming. And we will we'll catch you on the next time. This is nice too, because it's probably the shortest review, one of the shorter reviews I've done, and we hit an hour 30 pretty much perfect. So that's pretty nice. Let's go ahead and kill that, and thanks for watching, everybody. Have a wonderful time.